You always steal my thunder.
Does it look like I care?
I hate you.
Guys, we're live! Good morning, AP Physics.
Welcome to News from You.
I'm Anusha.
And I'm Omega.
Isn't it a great day for vision homework?
It sure is, Inertia. Vision homeworks are truly the highlight of my day.
Breaking news. There's been a massive collision between Vindelicious and Aquilanicious. So delicious. Dun dun dun!
Let's take a look. Here's a video from a live recorder on site.
Here we are at the scene of the crash. Oh my god! It's happening again! 911!
Our job is to figure out whether or not Aquila was speeding.
I wish we could consult Sir Isaac Newton.
I got him!
What? Where'd you get him from? Don't worry about it. Now, Sir Isaac Newton's gonna help us solve this problem.
So basically, my first law is that an object at rest will stay at rest until an outside force acts upon it. And since the only two forces are from the two cars, my third law tells us that the forces must be equal and opposite. Also, the impulse is equal and opposite for both cars. So this means that every interaction between the two cars is equal and opposite and can be expressed by this equation, which can then be rearranged to this equation. So let's apply this to the collision.
Alright, so Aquila's mass was 20 kg. We need to find her initial velocity, and we know her final velocity is 33.2 meters per second. For Vindia, her mass is 24 kg. She was at rest, so her initial velocity is 0 meters per second, and then her final velocity is 10.2 meters per second. So here we have our equation that we learned today, and then we plug in all our knowns. So our variable that we're going to be solving for is VAO. And then this can be crossed out because VBO is 0. We plug in all our knowns, and we calculate VAO, Aquila's initial velocity, to be 20.96 meters per second, which is over the speed limit, so she was speeding.
Well, in real life, collisions are much more complicated, and they involve angles.
Wow, what a coincidence. Another accident's about to occur.
It was a crash between a yellow car with a mass of 1,020 kilograms that was at rest, while a green car with mass 1,200 kilograms had an initial velocity of 42.6 meters per second traveling east. After the crash, the green car's final velocity was 35 meters per second at 53 degrees. The FBI wants us to figure out the angle and the final velocity of the yellow car.
In 2D momentum, the angles move in different directions in respect to the x and y axes. This also follows the rules of conservation of energy.
As you can see from the initial diagram, the green car is moving to the east at a certain velocity, and the yellow car is just standing there, it's at rest. And then after the collision, you can see in the final diagram, the green car is moving above the horizontal at an angle of 53 degrees, and then the yellow car is moving at below the horizontal at a velocity that we don't know yet because we're about to calculate it, and at an angle of we don't know yet because we're about to calculate it. So to find the final yellow car velocity and the final yellow car angle, we want to start with the x direction. Since this is 2D, that means there are two directions of momentum. So we're going to start with the x direction of momentum. So if you, the entire formula is the same as linear momentum, except it has angles. And for x, it'll have the cosine angles, and for y, as you'll see later, it'll have the sine angles. So if we want to start, we know that since the yellow car wasn't moving at all initially, its initial velocity is going to be 0. So you want to kind of just make that 0, and it can just go away because we don't love it. And then if you look at the initial green car velocity, the green car velocity, it does have an initial velocity, so it's not 0, but its angle with respect to the x-axis is 0 because it's moving east, so there's no angle, so 0. And cosine of 0 is 1, so you can just kind of ignore that. And then your final formula will be this. So once you have your final formula, you want to start plugging in your givens. So once you plug in all your givens, you get this. And then you want to put this in your calculator and then subtract this from this. And then when you divide that value by 1230, you're going to get 17.8595. And then once you find that, you can just kind of divide that by cosine of angle of y. And you'll get VFY is equal to 17.8595 divided by cosine of angle of y. And we're going to use that value in our y calculations, as you'll see in the next segment. So now that you found that, you can work with y momentum. As you can see, it's the same formula, but with sines instead of cosines. Now, for the initial y velocities, initial y velocity because this one's moving to the east and this one's not moving at all. So you can cancel these out and rearrange your formula to look like this. And then all you have to do is use all your givens and plug them in. And since you already found the final y velocity over here with the x's, you can plug that back in here. But you have to make sure to negate it only because as you can see in the final diagram, the yellow car is moving below the horizontal, meaning it's going down, so its y velocity is negative. So once you plug that all in, and you can find the y theta, and that you're going to get 2.218. And after you find the y theta, you can plug that back into this equation that you found to find the Fy, and the final yellow velocity you get is 17.872.
So can momentum and impulse be applied to calculus?
Yeah, of course. Newton can explain that to us. Where's Newton, though? Newton!
Oh,
okay.
I'm back, baby. Well, it seems like my second law can help us out with this, which tells us that force is equal to mass times acceleration. And since force is equal to mass times change in velocity over change in time, and since change in momentum is equal to mass times change in velocity, what we really have here is force is equal to momentum over change in time. And after rearranging that equation, we get impulse, which is the integral of f dt. Therefore, impulse is the change in momentum.
So let's apply what Newton taught us to this problem. So here we have the force of a car with respect to time. And now we have to find impulse. So according to Newton's second law, we know that the integral of f dt is equal to impulse. So let's find that using this graph. So here we have this beautiful shape. What we can do is split it into three separate shapes. A triangle over here, a rectangle, and a triangle. So the area under the curve is what an integral is. So let's find the area under this curve. So what you can do is 1/2 base times height for the first triangle, then base times height for the rectangle, and then 1/2 base times height for the second triangle. So we took the area under the curve, and to find the exact value, we split it up, and then you have the base of the triangle, which is 2 seconds, and then the height is 6 newtons. For the rectangle, the base is 2 seconds, the height is 6 newtons, and then the same for the second triangle. So that gives you the overall impulse, which is 24 newton seconds. So since impulse equals the change of momentum, we can use the area that we found under the curve of 24 newton seconds and set that equal to the change in momentum. So we have the mass and initial velocity of -3.2 meters per second, so we can solve for VF of -3 meters per second. It's okay for velocity is negative because that just means it's going in the other direction.
Thank you so much for all your help. For the best. Yes. Why, it's my pleasure to spread sciences to all the time periods. It's just what I do.
He is an imposter. What? An imposter!
See, about that.
It's time to go. Someone get him!